Any big plans this weekend? No? Anybody doing anything at all this weekend? What's that? Writing papers. Well, I have an exam this weekend. I hope I do well on it. Y'all have stuff coming up next week? Anything? Y'all have an exam in this class, right? Do you have any other exams next week? What do you have? Biology lab. You too. Are they tough, or is it sort of like the physics lab, where it's easy? It's tough, yeah. All right. Well, again, I don't advocate doing stuff over the weekend, but if you need to work this weekend, be useful in it. Um, let's see, the test for us next week will cover just chapters 5 and 6. Have I told y'all that? It's chapters 5 and 6. So you'll see work of a variable force, you'll see conservation of energy, you'll see momentum, you'll see 2D collisions, you'll also see what we're going to get in today where we have elastic collisions, where not only is momentum conserved, but also energy is conserved. So we'll get into that in just a little bit, but let's try this quick test problem. We worked a very similar problem last time. Oh, this quick test problem. Um, worked a very similar problem last time with the dodgeball clip. Need to calculate the final velocity of White Goodman, assuming as we did before that when the ball strikes and the ball goes to zero velocity. Hey, Shane. All right. Let's do about 10 more seconds. I'll stop at 225. 225. Just guess if you're not sure. All right. A is right. I um I start with this idea that the initial momentum equals the final momentum. These are vector quantities. The object that's moving initially is just the ball. Uh, so you have two things in this system. You have the ball and you have White Goodman. And initially only the ball is moving. So its momentum is 0.5 kilograms times its velocity, which is 10 meters per second. That's going to equal the final momentum, which is going to be White Goodman, which is 100 kilograms times its final velocity, 5 divided by 100 is VF. That's 0.05, 500ths. A is the right answer. Let's see, let's try another problem. Oh, we're going to do multidimensional problems, or multidimensional collisions. so far all we've done are 1D collisions, but 2D collisions aren't really that much more complicated. It's just a little bit more algebra to solve the equations. So in these 2D collisions, you consider the momentum in each of the three dimensions. Momentum is conserved in the x direction, momentum is conserved in the y direction, and momentum is conserved in the z direction. I want to remind you that our x and y components uh, of our velocity, Vx, is equal to V cosine theta, and Vy is equal to V sine theta. You'll need to remember that from our previous, what was that, chapter 2 or whatever, but I think that you've got that down by now. Our x and y components of our velocity, uh, and we're actually not going to do the z component. The z component is a little bit more complicated. You need a couple of different angles to discern that. So we won't mess with that. We'll just do 2D collisions. Let's look at a couple particles. I have these particles. They have their initial velocities given and their final velocity given here. And I want to know what is the final velocity of that second particle. Now in this case, I give you the velocity in IJK notation, so it becomes a lot simpler because you don't have to deal with the cosine and sine theta terms. But for example, if I gave you this, V1 would be let's see. So for example, if I gave you V1 would equal to 4.12 meters per second at an angle of theta equal 0.25, 14 degrees below the plus x-axis. If I gave you that, then you would just find what are the x and y components of the velocity. So the x component of this 4.12 times the cosine of 14 is 4 meters per second, and 4.12 times the sine of 14 is negative 1 meters per second. Negative 1 because it's below the x-axis. You follow me on that? Yeah. Okay, let's work through this problem. We'll see another in just a bit. Likely, if you have a 2D collision, I'll give you the IJK notation for the velocities. Okay, so I know that my initial momentum is equal to my final momentum. So I'm going to start with first my x momentum is equal to the final momentum. So that's going to be m1 v1 final in the x direction plus m2 v2 final in the x direction. And then it becomes working out the same problem as we had before. So M1 was 2 kilograms times V1 initial. See, I'm going to make this smaller. You see that okay? Yeah. All right, so 2 kilograms times V1 initial, which is 4 meters per second. Now that is this x component of my initial velocity plus M2, which is 4 kilograms, times V2 initial, which is negative 1. That was this velocity. Notice it's just in the x direction. That's the final velocity. Oh, no, I'm sorry. That's the initial velocity. Equals to m1, which is 2 kilograms, times negative 3, plus m2, which is 4 kilograms, times v2f in the I direction, or the x component, rather. Okay, and then you solve for v2fx. When I solve for that, I get 8 minus 4 on the left-hand side. That's 4. Negative 6 plus 4 v2fx. And so that's 4 over negative 6, or 410 divided by 4 equals v2fx. So v2fx equals, what's that, 5 halves, 2.5. Now that's just the x component of the velocity, and then you have to do the same thing to solve for the y component of the velocity. I'll do that here in just a second. But let me step back through what we did so far. This is just setting the x components of the momentum equal to one another. The initial momentum in the x direction is equal to the final momentum in the x direction, here and here. And then I can write out my terms. I have two particles that are involved. Initially, the first particle in the x direction has 8 kilogram meters per second of momentum. The second particle in the x direction has negative 4 kilogram meters per second. In the final state, I have negative 6 for the first particle. That's the final momentum only in the x direction. It also has another component in the y direction. And then I'm looking for that v2fx. I solve that for v2fx and I get 2.5 meters per second. It's a positive velocity. And now for the next step, I need to solve for v2fy. But it's really the same thing again. So you see, this problem is basically identical to the problem we worked before, except it has two steps to it. I have to solve for both the x and the y component. Let's solve for that y component. Um, so I do the exact same thing again. This is the y component. I say that p initial in the y direction equals p final in the y direction. That's going to be m1 v1 initial in the y direction plus m2 v2 initial in the y direction equals m1 v1 final in the y direction plus m2 v2 final in the y direction. And I'm now solving for this term. I'm going to go ahead and solve it, like write the, well, I'm going to do the numbers. It's easier here because the numbers are easy. I need y'all go ahead and take a minute actually and solve for v2fy. I got a value for v2fy. Shane, you got it? 0.5 is right. That's what I got too. Is that what y'all got? So the key here is to make sure that you get your components right. Notice here I'm getting the y components of those initial velocities. Um, m1 is 2 kilograms. v1fy was negative 2 plus m2. See, that's 4 kilograms. And then I saw that I have negative 2 over here equals negative 4 plus 4 times v2fy. And I solve that, I get v2fy is 2 over 4 or 0.5. So if I was going to report my final velocity of that particle, v2f, it would be, what was the first one? It would be 2.5 plus, that's in the I direction, plus 0.5 in the j direction. Remember, if I asked you the magnitude and direction, y'all could do that. Find the magnitude and direction of this velocity vector. I could ask you that, so make sure that you're up on that. If I want to know the final velocity, v2f, I would say that it's the square root of 2.5 squared plus zero point 0.5 squared. Let's see, what is that? I get 2.55 at an angle of 0.5 over 2.5 arc tan. I get 11 degrees. You'll get the same, Beans? Do you get 11? Yeah, at 11 degrees above the x-axis. I know it's above the x-axis because both components are positive. All right, be prepared to do that too. You'll definitely see, well, I say definitely. I haven't made the test out yet, but that's something you need to know how to do is 2D collisions. Conservation momentum in 2D collisions. Just like 1D, except you're just throwing in some vectors there and just separating the x and y components. See, I think I have another problem for you to try on your own. I'll try to give you easy numbers on it so you're not bogged down in the numbers. You'll try this one on your own. Here I have two particles. Initially, one of them's at rest, the other one's moving. Uh, oh wait, no. Hold on. Oh yeah. So I also give you the velocity of the second particle, and I want to know the final velocity of the first particle. See, I'll try that one out on your own. I'll give you a couple minutes. Remember, you want to separate the x and y components of the momentum. Okay, keep working. I'm going to start writing a few things up on the board. So I got 2 meters per second for the x component, right? And then I do the same for the y component. You're still working on. Let me explain what I did over here, though. Said my initial momentum in the x is equal to the final momentum in the x. Initially, that first particle is traveling at 3 meters per second in the x direction, so this is its x momentum. The first particle is not moving at all, so it's 0. Then I'm looking for the final velocity of the first particle, and I'm told in the problem that the second particle is moving at a half a meter per second in the positive x direction. So the only velocity, the only momentum that the second particle has is in the x direction. And then I solve this for VFX1. That's the x component of the final velocity of the first particle. I do the same thing over here. 2 kilograms where is it? Times -4, right? Was it -4? Yeah. Times -4 meters per second. So now I'm looking at the y components here. It's negative plus 0, because that second particle is not moving at all initially, is equal to m1, which is 2 kilograms, times v1 fy plus 0. Why 0 in that second term? Right, so because this particle right here has no velocity in the y direction, it only has this half a meter per second in the x direction. All right, and then I have -8 equals 2 v1 fy. So v1 fy equals -4. So if I'm going to write v1f, I'll say v, the final velocity of particle 1 is 2I plus 4j. If I asked you for the magnitude of that, it would be the square root of 20. Would it be negative? It would be -4. Thank you. Sorry about that. The magnitude would be the square root of 20. The angle would be the inverse tan of 4 over 2, which is get 63 degrees. Where is that? Which quadrant is it in? 63 degrees where? In the first quadrant? The third quadrant? The fourth quadrant, right. So that's in the fourth quadrant. Because my y component is negative, x is positive, y is negative, so it's over here. So it's 63 degrees below the plus x axis. It's in the fourth quadrant. Well, it helps me to draw a picture whenever I see vectors like that. Okay? Good test question, something like that. I try to keep the numbers simple, just really seeing that you can apply the conservation momentum in 2 dimensions. A little bit of vector stuff coming in there. Okay? I could do that on a test right now? I think you probably could. All right, we're going to look at collisions. We have one more type of problem that we're going to look at, and that's the type of problem in an elastic collision. Elastic collisions, not only is momentum conserved, listen, in every collision that ever occurs in space or time, momentum is always conserved. Momentum is conserved in every collision. In a special subset of collisions, we also have energy conserved. Energy is conserved when what type of forces are at play? Conservative forces, right? That's what we call conservative forces. They conserve energy. There are only a handful of forces that truly conserve energy, and those are what type of forces? Okay, yeah, gravitational forces. I'm sorry, who said that? Just heard a voice. Okay, no idea what I said. All right, gravitational forces and electric forces. Those are field forces. Any type of force that doesn't require contact is going to be a conservative force, because whenever you have contact, you can lose energy. So in elastic collisions, both momentum and energy are conserved. And all that means is that no energy is lost. Momentum is always conserved, but in these elastic collisions, no energy is lost. There aren't many examples of this. What's a good example of an elastic collision? Chemists out there? Gas particles. So whenever you have a gas in a container, those particles, they move around a lot in the container. They never actually touch one another because when they get close to one another, they do like this, right? Because those electric charges cause them to bounce off of one another. So the collision of gas particles is a good example. There aren't many other examples, but that's a good example. But we can also approximate some collisions as elastic, and we often do this. For example, like billiard balls, when they collide, because they're really hard and they don't deform very much, when they collide, they basically lose no energy. You lose a little bit of energy to friction or sound that's produced, but for the most part, we consider those to be elastic collisions too. But a true elastic collision, no energy is lost. So in these, momentum is conserved. That means that Pi is equal to Pf. That's our law of conservation momentum. But energy is also conserved. That is that Ei is equal to Ef. If we're talking about gas particles, really the only energy that they have are kinetic energy. We'll see a problem like that in just a bit, where not only do I have the initial and final momentums are the same, but also the initial and final kinetic energies are also the same. And in elastic collisions, only momentum is conserved. Energy is not conserved. And these are most collisions. So you run into somebody out in the quad, you bump into them, that's an inelastic collision. If you have a car crash, two cars bump into one another, that's an inelastic collision. Lots of energy that's being lost there. Okay? So next time you're out in the quad, you go bump into somebody and say, hey, sorry for that inelastic collision. Okay? And then you'll never forget that inelastic collisions. These are basically all other collisions. Momentum is conserved, but not energy. You lose energy in those collisions. We've gotten into punch buggy. Y'all play punch buggy? Y'all do play it? Like our family, we play it religiously. We're always on the lookout for a VW bug. And then we hit one another in the arm. Not too hard, but a little bit hard, like enough to make it feel. Enough to make it fun, right? When I was a kid, we had bruises all over our arm because between my house and the town, the nearest town, there was a VW junkyard, and they must have had like 100, like 100 bugs. And so I had two older brothers, so they were 6 and 8 years older. So man, we would go, and I tell you, inelastic collisions all over the place. Boom, 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 boom. I'd be all black and blue. Parents never did anything. You can also have a subset of inelastic collisions. This is just when the particles stick together. In a perfectly inelastic collision, it's inelastic, but the particles stick together. It actually makes it a lot easier to work when the particles stick together um, because they stick when they collide, and when they stick, they both have the same final velocity. So it makes it a little easier to work out. Let's see, I have an inelastic collision on this next problem. Oh, because this is inelastic, momentum is conserved, energy is not conserved. Let's try this out. It works the same way as we did before. It's actually a little bit simpler. You just have fewer terms to deal with. Uh, so before collision, after collision, there's my particles, there's their velocities. I want to know what is this final velocity. Just start out by saying Pi is equal to Pf. You want to break up your x and y components, remembering that these two particles are now going to have a combined mass of what? 6 kilograms. They stick together, so you just treat it as one 6-kilogram particle and find the x and y components of the velocity. Go ahead and give that a shot. going to start writing it up here. I got 2/3 for VFX. Y'all agree with that? 2/3. It's positive. Careful on this next part. What is my y component of the momentum for the second particle? Is 0 because that second particle is not moving in the y direction. So this is 4 times 0. Again, because this particle right here only has an x component. Notice this is the y component of the first particle, or the velocity. I get negative 1/3. Y'all get the same? So in final vector notation, v final is 2/3 I minus 1/3 j. And you can go through and do the vector, the magnitude and direction if you want. Okay. Let's look at inelastic collisions. Let's see. Oh shoot, I forgot to bring my 2 little balls. I'll bring it next time. You don't have a separate page for this, but it's stuff that we've done before. So you should have a blank page on 202. Elastic collisions. Remember, momentum is conserved. P initial equals P final. And energy is conserved. Energy initial is equal to energy final. We'll do a very simple one of this because if you have a really complicated set where you have motion in the x and y directions and you have more than 2 particles, they're solvable, but they're really difficult to solve because you get a bunch of equations. So we'll just do a simple one, but just know that you can extend this out to however many particles that you want, however many dimensions that you want. Because when you have this extra set of equations, you can solve for more unknowns. All right, so let's say that I have 2 particles. I have a 1 kilogram particle traveling at 2 meters per second in the x direction. That's its initial velocity. And then I have another particle, a 2 kilogram particle, that has an initial velocity equal to 0. So v naught of this one is 0. And then I want to know what is the final speed of both particles. They undergo an elastic collision. That means they just bounce off one another really well. You can think of them as billiard balls. These would be some honking billiard balls. But just 2 particles, they collide elastically, however they do that. Maybe they have electric charges on them and they just bounce off one another or whatever. But anyway, they collide elastically so that no energy is lost. All right, so I'm going to have 2 sets of equations. I'm going to be able to say that the initial momentum is equal to the final momentum. That is that m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. If you want to put in the numbers at this point, that's fine, because I made it with simple numbers so that the algebra works out very simply. Well, let me just point out to you that we have two unknowns in this equation. I don't know anything about the final velocity, so I can't solve this equation in and of itself. There's no way for me to solve it. I just don't have enough information. But because I know that this is also an elastic collision where energy is conserved, I can write a similar equation saying that 1/2 m1 v1 initial squared uh, equals or plus I know that the initial energy equals the final energy. And again, we're talking about gas particles. Gas particles don't really have gravitational potential energy because their masses are so small. And we'll consider the same here, that all this occurs on a one-dimensional plane so that the height of the objects don't change, so the potential energy doesn't change. That would be true for gas particles, though obviously these aren't gas particles. Um, so I can get rid of some terms just because of the way the math works out. I know that any initial term here is going to go away, so this one goes away and this one goes away. Also recognizing that I have two unknowns here and here. Well, look, I have a system of two equations, two unknowns, so we can solve that, right? I'm just going to sub one of them into another. Um, I'm going to solve this equation on the left for V1F. And then when I do that, I'll sub it in up here on this equation and then solve that equation for V2F. So I have V1F equals M1 V1 initial minus M2 V2 final divided by M1. I'm going to go ahead and put some numbers in here. I get 1 times 2 minus 2 times V2F divided by 1. That's 2 minus 2 V2F. Okay, and now I'm going to plug this in here and solve it. All right, so I have, I'm going to go and put in some numbers. 1/2 of 1 times 2 squared equals 1/2 of 1 times 2 minus 2 V2F squared plus 1/2 of M2 V2F squared. Okie dokie. So it's the algebra here that's going to get you. You sort of have to be very careful with your numbers. And again, I try to give you simple numbers so that the algebra is a little easier. 1/2 of 1 times 4 is 2. This is 1/2. If I FOIL that out, it's 4 minus 8 V2F plus 4 V2F squared plus V2F squared. Okay, and then I have to solve this. Uh, distribute that half. I can get rid of these 2's, subtract 2 from both sides, and I'm left with this. I have 0 equals 3 V2F squared minus 4 V2F. All right, how many solutions are there to this equation? There are 2, right? Y'all know how to solve this? What would I do? What's my next step? What's one of the solutions to this equation? 0, right? So if I have V2F equals 0, then that is a solution. I also have another. I can find that by factoring out of V2F. And then I solve this. I say 3 V2F minus 4 equals 0 and solve that for V2F. So V2F can either be 0 or it can be 4/3. We don't have any way to tell which it is. All right, and then if I want to find V1F, I can come back up here. I say V1F equals 2 minus 2 times 4/3. That's 2 minus 8/3. That's negative 2/3 meters per second. Okay, the algebra gets a little complicated on that, but this is about as simple as I can make it. What if I did this like as a take home so that you could do it on your own and then bring it into the test? I'm not going to make it that much work, very much, maybe 10 points or whatever, because the algebra, like I said, the algebra in a test, half the time I get it wrong, so y'all probably get it wrong too. But I'll give you a problem and I'll send it out to you uh, today, and then you'll just bring it into the test with this worked out. Y'all do that? A take home problem? It'll be an elastic collision. It'll be something similar to this. Work through it. All right. Make sure you get the right answer. It's a lot easier if the answer's right. Y'all can do that? Okay. Let's see. Let's do some more concept test questions. You might know where we left off here. We've done some, I think. We didn't start chapter 6 at all? Ah, shoot. Okay. I'm sorry about that. I should have. An open cart rolls along a frictionless track while it is raining. As it rolls, what happens to the speed of the cart as the rain collects in it? So remember, momentum is always conserved. So this object has a certain momentum initially. Rain falls into it. And what happens to the speed of the cart as this rain falls into the cart? All right, I'll stop at 1 minute. 1 minute. All right, C is right. It's going to slow down because, hold on, give me a second. It's going to slow down because our momentum is conserved. Our momentum is our initial momentum equals our final momentum. That's the mass times the velocity. Initial is mass times velocity final. But here, notice that the mass goes up, and since the momentum has to be conserved, that means the velocity has to slow down. So usually when we have objects that are changing a momentum, their velocity is changing, but sometimes their mass can be changing too. And really, when we look at Newton's second law, F is equal to dp dt, often we'll write that as it's equal to m dv dt, but really it's the derivative of m times v with respect to time. So either that d can act on the m or it can act on the v. Now usually the mass doesn't change, but either the mass or the speed can change. And that's what we have here. The mass is changing, which is causing it to slow down. A system of particles is known to have a total kinetic energy of 0. What can you say about the total momentum? Stop at 40 seconds. 40. Okay, good. We know the momentum is 0 because if the kinetic energy is 0, remember kinetic energy is scalar or vector quantity? Energy is always a scalar. And so that means it doesn't have directions. So if our energy is 0, that means that the objects cannot be moving at all. So if they're not moving, that means the momentum is 0. How about if their momentum is 0, does that mean that the kinetic energy has to be 0? Does it follow that the kinetic energy has to be 0 if the momentum is 0 of a system of particles? I'll stop at 35. 35. B is right, because the momentum can be 0 either because the particles aren't moving or because they're moving with equal momenta in opposite directions. And then that total momentum would equal to 0. They would add up because they're vector quantities. Two objects are known to have the same momentum. Do they necessarily have the same kinetic energy? Stop at 30 seconds. 30. D is right because P is equal to mv, and kinetic energy is 1/2 mv squared. So they can have different masses and velocities, but still have the same momentum. Like, for example, I could have 2 times 4, or I could have 4 times 2 for the momentum, but these would give very different kinetic energies. The one with the higher speed would have more kinetic energy. A net force of 200 newtons acts on a 100-kilogram boulder. The same force acts on a 130-gram pebble. How does the rate of change of the boulder's momentum compare to the rate of change of the pebble's momentum? Remember, by Newton's second law, F is equal to delta P over delta T. So how does their rate of change of momentums compare? I'll stop at 110. 110. Okay, we're sort of all over the board. Um, What is a rate of change of something? If I say the rate of change of something, what does that tell you? I have to say the rate of change of position. What is that? That's the velocity, right? Whenever I say a rate of change of something, it's that quantity over a change in time. So if I'm talking about a rate of change of momentum, that simply is this. It's a rate of change of momentum. How does the momentum change with time? And so since by Newton's second law the force is equal to the rate of change of momentum, how do the how do the rates of change of momentum for these two objects compare? How do their forces compare? They have the same force acting upon them. Since they have the same force, they're also going to have the same rate of change of momentum. So C is the right answer here. That's sort of really just thinking about the language, but whenever you see rate of change of something, that's referring to how that thing changes with time. Okay, here we have a net force, acts on a 100-kilogram boulder, same as we had before. But how does the rate of change of velocity compare to the rate of change of the pebble's velocity? And we have F is dp dt. Let's go to 45, 5 more seconds. Just guess if you don't know. That's right. So this is sort of more intuitive, right? That I apply this force to the boulder, it's going to accelerate at a lesser rate than does the pebble. So B is the right answer here. A small car and a large truck collide head on and stick together, like their bumpers stick together or whatever. Which one has the larger momentum change? The car, the truck, they both have the same, or you can't tell without knowing the final velocities. Remember that F is equal to dp dt. Which has the larger momentum change? That would be dp, or delta p. All right, I'll stop at 50 seconds. 50. 5 more seconds. Okay, C is right. Newton's third law, right? They both have the same force. That force occurs in the same amount of time, so they're both going to have the same change in momentum. We'll pick up with this. Listen, next time, y'all, I'll send out that take-home problem today. Next time, we'll finish this up. We might go and start on Chapter 7, but also if you have questions for the exam, we can spend some time reviewing that. So we'll finish this up, then we'll take care of your questions, and then if we have time at the end, we'll start on Chapter 7, but Chapter 7 will not be on the test. Okay? You have a great weekend. I'll see you next week.